Question number 1. Work done to bring a unit positive charge. Though it should be written work done to bring a unit positive charge per unit charge, but it's okay. Unit positive we can regard as per unit charge. So this is potential. Option D. Question number 2. Charge particle is projected along the axis of the current carrying loop. So this is current carrying loop. This is current carrying loop. And charge particle is being sent along the axis of the loop. So this is velocity. And magnetic field is also along the axis only. Okay, either away from axis or towards the axis. That depends upon the direction of the current flowing through the loop. So B and V are parallel. So there will be no force because it is parallel. So 0 degree, and force on the magnetic force on the charge will be 0, and hence no force, and hence no change in velocity. So the charge particle will move with constant velocity. Now let us see question number 3. In question number 3, 4 diagrams are there, which is correct. So this one seems correct. Magnetic field inside the bar magnet is south to north inside and north to south outside. So this is correct. Question number 4. When is the effective capacitance of capacitor increase? So capacitance is sum of individual capacitance in parallel. So it increases in parallel. So option B. Question number 5. For metallic conductor, which is the correct graph for resistance versus temperature? So resistance increases for metals with increase in temperature, and it does not increase linearly. So this is a graph. Here it is linear increase, so this is not. And this is for alloys. Okay, so it doesn't increase linearly but increases. What is the question number 6? What is the formula for work done in rotating the dipole? So you know the work done or potential energy is given by minus mb cos theta 2 minus cos theta 1. So this minus will go inside and it will make this negative and the other one positive. So cos theta 1 term should be positive. So this is cos theta 1, sorry. Cos theta 1 is positive here and cos theta 2 is negative here. So this one is correct. Now getting to the question number 7. Which of these is correct definition of electronic current? So electronic current means the current of movement of electron. So electrons move from negative to positive. So we will say that current flows from lower potential to higher potential. So this is electronic current means here. This question is not very clear though, but we'll understand it as electronic current means the current due to the motion of electrons. So electrons move from negative to positive. So electronic current is from negative to positive, yani lower potential to higher potential, and conventional current that is regarded as opposed to the direction of motion of electrons. So conventional current will be from higher potential to lower potential. So electronic current will be from lower to higher so far. Let us see the next question. Question number 8. I is given and EMF is given. So we have to tell the self-inductance. So you will use this formula. EMF equals minus L di by dt. This is the relation between current and EMF. So you have to find out self-inductance. So L is to be found, and this is given as 10 millivolt, that is 10 into 10 to the power minus 3, and L is to be found, and di is d by dt of I you have to do, which is 5 plus 16t. Now you have to differentiate 5 and 16t one by one. So differentiation of 5 will be 0 because it is a constant term, and differentiation of 16t, 10 into 10 to the power minus 3 equals L. So 16 you can take out, so it is dt by dt, so it is 16. So L is 10 by 16 into 10 to the power minus 3. You can divide and you will get something like 0.625 into 10 to the power minus 3. So you can choose the correct option accordingly, that is 6.25 into 10 to the power minus 4. So let us see the next question. Question number 8. In question number 8, 8 we have done. 9. Induced EMF always occurs whenever there is change in magnetic flux. True. Current always induces whenever there is change in magnetic flux. So current can induce only when the circuit is complete. So this is false. So first is true and second is false. So C. Let us see the question number 10. Paramagnetic material becomes a permanent magnet when placed in strong magnetic field. Yes. Paramagnetic material have large positive magnetic susceptibility. So this is true also and this is the reason also. So option will be A. For 3-point charges to be in equilibrium, they must be collinear. Yes. And one of these charges must have different polarity. Yes, that is also true. But this is not the correct explanation for them to be in equilibrium. So we can understand it this way. See, if I make them non-collinear, Q1, Q2, Q3, then let us talk about the force on Q2. Then 1 will repel Q2. So this is force on 2 by 1. And 3 will also repel Q2. So this is force on 2 by 3. So two forces are this way. So your resultant will be along the diagonal. So net force cannot be 0 in such situations when they are not collinear. So one thing we have understood, that the charges should be collinear to be in equilibrium. 3 charges. For instance, this is Q1, this is Q2 and this is Q3. Now let us talk about the force on extreme wala, that is Q3. So force on extreme, this Q3 by Q1. Q1 will repel it. So force on 3 by 1. And Q2, if Q2 is positive, then Q2 will also repel it. Then force cannot be 0 on Q3. So Q2 has to be negative. If Q1 and Q3 are positive, Q2 has to be negative in order to attract Q3 so that forces can be in opposite direction. This is force on 3 by 2. Forces can be in opposite direction so that they can be subtracted to make it 0. Okay, so first is true because they need to be collinear for charges to be in equilibrium. Second is also true that one of the charge has to have opposite sign. That is also true. But that is not the correct reason for them to be in equilibrium, because not only the charges should be in opposite direction, the forces should be in opposite direction, force on 3 by 1 and force on 3 by 2. Not only the forces should be in opposite direction, but they should be equal as well. So it has to be 70 Newton, it has to be 70 Newton, so that the net force on this can be 0, so that the charges can be in equilibrium. So it is depending upon the magnitude also. Magnitude of and force depend upon whom? Force depends upon the magnitude of the charges, like this distance square. So force will depend upon not only the nature but also the magnitude of the charges. So second reason is not correct explanation of the assertion, but it is true. So that will be the option. So we have done 11. Now let's see question number 12. So a battery that contains EMF E and internal resistance R, when connected across 12 ohm, get this much current, and when 25 ohm, then this much current. We have to find out the internal resistance and EMF of the cell. So you can write down the condition as, in first case resistance is how much? 12 ohm. And in second case resistance is 25 ohm. In first case current is 0.5 ampere. In second case current is 0.25 ampere. So you can use the formula of current. Current formula is net EMF by net resistance. So current formula is net EMF by net resistance. So I'll do here. So current in first case will be net EMF. EMF will be same, and net resistance will be internal resistance plus R1. And similarly current 2 will be EMF will be same, internal resistance will be same, and external resistance will be different. So put them equal. Put them equal as in find out E. E is I1 and then R plus R1. And similarly from this side E is I2 and then R plus R2. So now because they both are equal to E, so you can put them equal. So first current was 0.5 ampere. Internal resistance is not known. And first resistance was 12 ohm. This R1 was 12 ohm. So just write 12. And from here current is 0.25 I2. R is not known and external resistance was, you can see, 25 ohm. So now let us multiply. 0.5 into R is 0.5 R, and then 0.5 into 12 is 6, and then it is equal to 0.25 R, and then 0.25 into 25 is 6.25. So 6 को उधर ले जाओ and this will come this side. So you can subtract 0.5 R minus 0.25 R equals 6.25 minus 6. So what is left? 0.25. And what is left from here? 0.25 R. So R is 1 ohm. So internal resistance could be found. And internal resistance you can put in the formula of EMF. Like here, this internal resistance you can substitute here. And you can substitute I1. And you can substitute external resistance. So you will find out the EMF as well. So that EMF will come about to be 6.5 volt. So the answer is internal resistance is 1 ohm and EMF is 6.5 volt. So let us see question number 13. Question number 13 is permeability. Relative permeability is mu r. Mu r is given as 200 and current is this much, 1 ampere. We have to find out the magnetic intensity. So this is formula based. Magnetic intensity is Ni. Yeah, magnetic intensity is Ni. So you can calculate. You keep N is here, 2000 per meter. And I is here. N has been given and I has been given. So your H will come. Your magnetic intensity will come, which is N into I. And N has been given. Number of turns per meter per unit length. Number of turns per unit length is 2000. And then I has been given as 1. So it is 2000 ampere per meter. And then you have to find out the magnetic field in second part. Second part, magnetic field. See, magnetic field with air inside the solenoid is mu naught Ni. But if you are putting some material, like they have used core of material, so you have to write mu material. In place of air's permission, you have to take the material's permission. So mu m n I. Number of turns per unit length have been given. Current has been given. A mu material can be opened as mu r into mu naught. So you can substitute mu r, you can substitute mu naught, which is 4 pi into 10 to the power minus 7. And number of turns per unit length is given and current is given. You can substitute. So this will come as, I'm just telling, and you all can solve. So B will come as 0.50 Tesla. So you can calculate. Now let us see question number 14, which is a derivation. Deduce an expression for potential energy of the system of 3-point charges and hence generalize the result for system of n-point charges. So this is the derivation you can directly see from notes. Now let's see question number 15. Question number 15. Write an expression for torque acting on a current carrying loop. So that is Niba sine alpha. And you should tell what is alpha. Alpha is the angle between field and normal. Now first question is, a current carrying loop free to turn is placed in the uniform magnetic field. What will be the orientation relative to to be in equilibrium state? For this is torque, and to be in equilibrium, torque should be 0. That is sine alpha should be 0. That is alpha should be 0 or 180. So we can take 0. So alpha should be 0 or 180. But alpha is the angle between field and normal. So you can write field should be parallel to normal, but orientation is asked, so you should tell in terms of field and this coil. So because field is parallel to normal, so you have to minus 90 minus 0. So field should be perpendicular to coil. Yeah, you can say plane of coil. So this is how it was supposed to be told. Question number 2. Under what circumstances will the current carrying loop not rotate? So when torque is 0. Again, what is the meaning of torque 0? Sine alpha 0. And so same answer will come. Sine alpha 0, but you should leave your answer only in terms of field and coil. So this is the condition. Whenever the coil you can say, or plane of coil you can say, when coil is perpendicular to the field, magnetic field, then net torque will be 0 and it will not rotate. Question number 16 is force between two parallel wires, and then you have to define 1 ampere. So this is again a theoretical topic, you can see from notes. And this is mutual induction. So mutual induction also you can prepare from notes, but it has to be done twice for M12 and M21. Yes, so let us see the next question. State the laws of electromagnetic induction. So you have to tell all 3 laws, including Lenz's law. And then you have this question, numerical. Magnetic field of flux density. Flux density is magnetic field only. So this is B, 10 Tesla, and number of turns 50. Area is 100 centimeter square. So you can convert into meter square as you get it. Find the EMF if the coil is removed from the magnetic field. So magnetic field has been removed, so that means final magnetic field is 0. So earlier what we noted, we will make it B1 in 2 seconds. So timings has also been given. So you have to find out the magnetic this EMF. So this is simple. EMF will be minus d phi by dt, and your phi will be open as BA. BA cos theta you should write, but theta is fixed, and you can see here field is acting normal to the coil. Field is acting normal to the coil. It's written here. Because the field is acting normal to the coil, like this is the coil and this is magnetic field. So you can see field is acting normal to the coil. So where is the normal? Normal is here. I mean normal to the coil is like this. So the angle between coil and field they have given as 90 degree, but the angle between field and normal is 0 degree. So you can put here 0 degree, cos 0 is 1, so cos vanishes. So we are left with minus d by dt of B and A. So EMF will be, area can come out, it is d by dt with minus, of course. So time is given, area is given, you can substitute, and dB is B2 minus B1. Final magnetic field is 0, initial is given, so you can substitute and find out. Area you can put in meter square, timings were already given, and dB can be written as B2 minus B1, and final magnetic field was 0. Field is reduced to 0 or it was removed from field. Both means that final magnetic field is 0 and initial was given, so you can put the numbers and calculate. So this was your question number 18. So let us see the OR part. So you have to derive motional EMF by Lorentz force. So Lorentz force, you can see this motional EMF from notes. Okay, Lorentz force means you have to talk about magnetic force and electrostatic force here. So we have motional EMF by many ways, but this method was to be done. So can prepare from notes. Now let us see the next question, which is the B part. So here length is given, B is given, resistance is given, and velocity is given. So first part is induced EMF, so that is BLV. Put magnetic field, put L, and put velocity, you will get. And then current is EMF by resistance. This is EMF. B you put, L you put, and V you put, you will get EMF. And if you divide the EMF by resistance, you will get current. So answer of this question, 18th B part, will be 0.2 volt and the current will be 1 ampere. So you can solve it. Let us see the next question. Question number 19 is Gauss theorem's application of spherical shell, that you can do from theory. Question number 20 is case based. You can go through the entire paragraph. Okay, and bar magnetics replaced by solenoid of cross sectional area this much meter square में है. This is number of turns. And we have been asked the magnetic moment. Okay, magnetic moment is given. Current is to be told. So magnetic moment can be opened as NIA. Magnetic moment is given as 0.4. This. Number of turns is given as 1000. Area is given as this. So substitute, you will get I. So in this question, I will come as 2 ampere. Question number next. Magnetic moment of a current of a conductor, magnetic moment of a current I carrying circular coil of radius r varies. So magnetic moment, I just told you, it is Nia and area is open as pi r square. So what is the relation between magnetic moment and radius? It is r square. So it's D. Question number next. A bar magnet of length 2L and pole strength this. So what is the magnetic moment of a bar magnet? For a coil it is Nia. For a circular coil it is Nia, number of turns into current into area. And for a bar magnet it is Qm, that is pole strength into length of magnetic axis. So here pole strength is given as P and length is given as 2L. So it is P into 2L and directed from south to north. South to north it is. So you can see which is the correct answer. 2PL south to north. D. Question number 4. Magnetic moment for solenoid and corresponding bar magnet is equal. Then you have to tell moving coil galvanometer and what is to be done to make it scale linear. So we have to use radial field. So you should write about radial field in the concept that you can prepare from theory. If a galvanometer has resistance 49.5, so that is capital G. Range means full scale current is 0.05 ampere. What will be the value of resistance needed to convert into ammeter? So because it is a question of conversion of galvanometer into ammeter, so you have to connect a low resistance which is called shunt in parallel to the galvanometer, then only it can be converted to an ammeter. So shunt is to be found. You can denote it by R also, no problem. And then you have to convert to this range, that is capital I, 5 ampere. So when you connect a small resistance in parallel to the galvanometer, then it converts into ammeter. So this is full current. Through galvanometer we take Ig. So through upper arm, what is the current going? I minus Ig. Upper arm resistance is shunt. Lower arm resistance is galvanometer G. They are in parallel, so you can put the formula. That is voltage, because they are in parallel. So put voltage equal. Voltage across galvanometer is equal to voltage across shunt. Voltage across galvanometer is current through galvanometer, its resistance, and through shunt, it is current through shunt into shunt resistance. So you put everything is there with you. Ig you have, capital G you have, I you have, Ig you have. So you can put and find out the value of shunt. So shunt can be calculated this way. This was question number 21, and shunt will come as 0.5 ohm. So please practice on your own. Use mathematics and find out. Question number next, or wala question. By Savit's law, you have to find out the magnetic field. Axis, B axial is to be found. And then at the center, second part, and then you have to draw the field lines through a circular coil. That you can do. And law used to find direction, that is right hand thumb rule, you have to explain. Okay. In question number 21 part C, they are asking to compare the resistances in two cases. So I think in one case they wish to say galvanometer to ammeter, and other case galvanometer to voltmeter. So you should say a galvanometer can be converted into ammeter by connecting a very low resistance in parallel to it. This is how it is converted into ammeter. This is low resistance and this is called shunt. And here galvanometer can be converted into voltmeter by connecting a very high resistance in series to it. So what is the comparison of these two resistance? That resistance in case of galvanometer to ammeter is low, and here galvanometer to voltmeter resistance is very high, and then this low resistance is connected in parallel to the galvanometer and this high resistance connected in series. So this is how you can compare. And then in question number 18, Question number 18, part A, which numerical is there, EMF value is 25 volt. So kindly complete the work.